Now, we are discussing about VLE qualitative behavior. That is vapor-liquid equilibrium qualitative behavior. VLE means vapor-liquid equilibrium. One vapor phase and one liquid phase coexist in equilibrium. Now coming to introduction. Before going to the topic, we will discuss about introduction. Before presenting the mathematical formulation of the multi-component vapor-liquid equilibrium problem, it is pertinent to discuss some key features of typical vapor-liquid phase behavior. The description of phase behavior of vapor and liquid phases coexisting under equilibrium can be complex and difficult to visualize for systems containing a large number of chemical species. Thus, to clarify matters, it is useful to consider a binary system. Other than multi-component system, we have to consider binary system. We have to consider binary system. The considerations for such a system may in principle be a generalized to understand the behavior of component systems. However, we shall restrict ourselves to description of VLE of multi-component systems to the corresponding mathematical formulation. Vapor-liquid equilibrium is the state of coexistence of liquid and vapor phases. That means one vapor phase and one liquid phase. In the qualitative discussion, we shall focus on systems comprised of two chemical species because systems of greater complexity cannot be adequately represented graphically. It is difficult to represent graphically more than two systems. When n is equals to 2, that means number of components are 2. The phase rule becomes F is equals to 4 minus 5. We know the phase rule n minus 5 plus 2. We have to substitute in place of n with 2. Therefore, degrees of freedom is equals to 4 minus 5. Since there must be at least one phase, that means minimum or maximum number of phase rule variables must be specified to fix the intensive state of the system is 3. Maximum number of phase rule variables to fix the intensive state of the system is 3. Maximum number of degrees of freedom is 3. Minimum is 0. The three phases are pressure, temperature and mole fraction. That is pressure, temperature and mole fraction. All equilibrium states of the system can therefore represented in three-dimensional pressure, temperature and composition or mole fraction. Within the space, the state of the pairs of phases coexisting at equilibrium define the surfaces, that is pressure, temperature and composition. Therefore, degrees of freedom is equals to 4 minus 2. That is number of phases are 2. Vapor phase and liquid phase. Therefore, F is equals to 2. A three-dimensional diagram is shown here for VL. That is pressure, temperature and composition. A three-dimensional figure represented for VLE, that is pressure, composition and temperature, are shown in here. Now coming to description of general vapor-liquid equilibrium behavior. The figure represents the pressure, temperature and composition surfaces which contain equilibrium states of saturated vapor and saturated liquid for a binary system. Lower surface contains saturated vapor, that is pressure, temperature and Y1 surface. Upper surface indicates saturated liquid, which is represented with pressure, temperature and X1. Here X1 is the liquid phase mole fraction, Y1 is the vapor phase mole fraction. These surfaces intersect along the lines UBHC and KAC2, which represent the vapor pressure versus temperature curves for the pure species 1 and 2. That means here we have to consider a binary system. That's why we have species 1 and 2. However, the lower and upper surfaces form a continuous rounded surfaces across the top of the diagram between C1 and C2. C1, C2 are the critical points of pure species 1 and 2. The critical points of various mixes of two species lies along the line rounded edge of the surface between C1 and C2. This critical locus is defined by points at which vapor and liquid phases coexist in equilibrium become identical between the critical points. Here, the subcooled liquid region lies above the upper surface, which is shown in figure. The superheated vapor region lies below the lower surface. The interior space between the two surfaces, that means superheated vapor region and subcooled liquid region, is the region of coexisting of liquid and vapor phases. If one starts with point at F, which is shown here, and reduces the pressure reduces at constant temperature. Here temperature is constant and composition along the vertical line FG. The first bubble of vapor appears at point L, which is lies on the upper surface. The point L is the bubble point. Bubble point definition is first bubble forms from the vapor, that is called as the bubble point. Thus, the upper surface is the bubble point surface. Here L is called as bubble point. The surface above the bubble point L is called as bubble point surface. The state of the vapor bubble in equilibrium with the liquid L must be represented by a point on the lower surface at temperature T and pressure of L. At the temperature and pressure of L. This point is indicated by V. Line VL is the tie line, which connects the points representing phases in equilibrium. Tie line is called as connecting the two phases in equilibrium. Here, line VL is the tie line. As the pressure is further reduced along the FG, more and more liquid vaporizes until the W, the process is complete. Thus, W lies on the upper surface and represents a state of saturated vapor having the mixer composition. Since W is called as the dew point, W is called as the dew point. The dew point is defined as the last drop of liquid disappears. It is called as dew point. Since W is the point at which last drop of liquid disappears, it is a dew point and the lower surface is the dew point surface. After the dew point, the surface is called as dew point surface. Further, continuous reduction in the pressure which leads to the superheated vaporization. Because of the complexity of 3D diagram, the detailed characteristics of the binary vapor-liquid equilibria are depicted in two-dimensional graphs, which is cut into two parts of three-dimensional diagram. That is Pxy and Txy. The three principal planes, each perpendicular to one of the coordinate axes, are shown in figure. Thus, the vertical plane perpendicular to the temperature axis, which is here, is outlined as ALBDA. The lines on this plane form Px1, y1 phase diagram at constant temperature, which is shown in two-dimensional diagram. That is figure A. Here there is three different temperatures. This is the Pxy diagram. If the lines from several such planes are projected on single parallel plane, a diagram is shown in A, which is the Px1, y1 plane at three different temperatures. The temperature TA represents in first figure, that is three-dimensional figure, indicated the area ALBDEA. The horizontal lines are tie lines, which are shown in figure E. The horizontal lines are tie lines connecting the compositions of phases in equilibrium. The temperature Tb lies between two species critical temperatures identified by C1 and C2. The temperature Tb lies between the critical temperatures C1 and C2, which are shown in three-dimensional diagram, and the temperature Td is the above both the critical temperature, that means above the C1 and C2. The curves for these two temperatures therefore do not extend all the way across the diagram. However, the first passes through one mixer critical point and the second through two such points. The temperature Tb indicates the area between the temperatures C1 and C2, that is critical temperature. Td is the above critical temperature in diagram 1, that is 3D diagram. All the three of the critical points are denoted by the letter C. Each is the tangent at which horizontal line touches the curve. Horizontal line touches the curve. This is so because all tie lines connecting the phases in equilibrium are horizontal tie lines. The tie line connecting identical phases must therefore be the last line to cut the diagram. A horizontal line passes through the three-dimensional diagram perpendicular to the p-axis is identified by critical temperatures C1 and C2 in 3D diagram. The temperature TD is above the critical temperatures. That is above the C1 and C2 temperatures. The horizontal planes passed through three-dimensional diagram perpendicular to the p-axis is identified by the area HIJKLH, which is viewed from the top, that is Tx1 y1 diagram, that is shown in figure B. When lines for several pressures are projected on parallel planes, that is at three different pressures PA, PB, PD. The resulting diagram is drawn in figure B. This figure B is the analogous of the figure E, except the values of temperatures are replaced with pressures. Other possible plots for mole fraction Y1 versus liquid mole fraction X1 either at constant temperature or constant pressures. The third line identified in 3D figure vertical and perpendicular to the composition. The critical point of a binary mixer occurs where the nose of the loop, this one, in this figure, is the tangent to the envelope. Put another way, the envelope curve is the critical locus. This third figure indicates the location of the critical point on the nose of the loop varies with composition. For a few species, critical point is the highest temperature and highest pressure at which vapor and liquid phases coexist in equilibrium. But in case of mixer, it is neither happen. Therefore, further decrease in pressure, condensation process occurs at this certain conditions. Consider in the figure enlarged nose section of the single pressure and temperature loop, which is shown in figure 4. The critical point is C, which is here. The points of maximum pressure and maximum temperature are identified by MP and MT. The interior dashed curves, that is here, indicate the fraction of the overall system, that is liquid in two-phase mixture of liquid and vapor. That means mixture of both vapor and liquids. To the left of the critical point, that is this one. A reduction in pressure along a line BD is accompanied by vaporization of liquid from bubble point to dew point. However, if the original condition corresponds to point F, a state of saturated vapor liquefaction occurs, further reducing the pressure, and which reaches the point G, after which vaporization takes place until the point reach, that is dew point and H. This phenomena is called as retrograde condensation. It can be important in the operation of deep natural gas wells where the pressure and temperature in the underground formation are at conditions represented by point F. Generally, in the operation of deep natural gas wells, pressure and temperature in the underground formation are at conditions represented by point F. If the pressure at the wellhead is that of indicated by point G, which is liquefaction of the product stream is accomplished along the partial separation of the mixers. That is heavier species of mixers. Within the underground formation itself, the pressure tends to drop as the gas supply is depleted. If not prevented, this leads to the formation of a liquid phase and consequent reduction in the production of the well. Repressuring is therefore a common practice, that is a lean gas, which means gas from which the heavier species have been removed. Lean gas is returned to the underground reservoirs to maintain an elevated pressures.